fantastic way to help us understand how light is moving is to use a ray diagram. So let's talk lenses ray diagrams. What we will notice is that the same rules that we were applying for mirrors, I have a similar set of rules set up for you here for applying to lenses. We're still going to have our primary axis, we're still going to have the object, and we're going to have lenses labeled. But you're going to notice that um, the focal length and vertical focal length are labeled for you, and they are on different sides, the opposite sides that they were for the mirrors, because the lenses do an opposite thing. The incident rays will still run parallel to the primary axis, starting at the tip of the object, and will always start at the tip of the object. Transmitted rays now will start from the center of the optical device, the lens, which is where the incident ray will terminate, and will go through the actual focal point for our convex lenses and through the virtual focal point if we have a concave lens. The second incident ray is going to use the opposite focal point of what the transmitted ray used. And the second transmitted ray is going to run parallel to the primary axis, and the image will appear where the transmitted or refracted rays actually meet. Okay, so as with everything, it makes way more sense when you're actually doing it. You do have access to this PowerPoint. Please use it, put it into um, slideshow mode and use the animations so you can go along with this. So we're going to place the object outside C. And if you remember, C is twice the focal length, and I don't have them demarcated on your diagrams. I would say if you're trying to go for outside C, place it way far away from the focal point. And you can even use your fingers to like do a quick measurement of where C would be located. So our first incident ray is going to start at the tip of the lens, tip of the object, the arrow, and run parallel to the primary axis or horizontal and stop at the center of the lens. Yes, I know there is refraction as it enters the lens. It's going to move through the lens, and then geometrically there'll be a new angle of incidence and then refract out. Geometry wise, everything works out if we use the center of the lens, the part that runs directly through the vertex. So if the first incident ray entered parallel, this first transmitted ray is going to exit diagonally using the actual focal point because a convex lens focuses the light. Lenses, unlike mirrors, use both the focal point and the virtual focal point in creating their um, ray diagrams. So the second incident ray is going to connect the tip, the focal point, virtual focal point, and the center of the lens, stops at the center of the lens, and then will be transmitted parallel to the primary axis. And you can see where the two transmitted rays meet is where we'll see the tip of the arrow. Okay, now for the concave lens, again, we'll put the object outside of C, far, far away. We'll draw in our incident ray connecting to the center of the lens, running parallel to the primary axis, but we're going to use the virtual focal point, because it diverges light, to aim our transmitted ray. So if you notice, these would be in a perfect line. If you have your ruler, you can put it on the screen and see that. Then the second incident ray is going to use the actual focal point as its aiming device to line everything up so that we get the correct diagonal line. But with everything, incident rays must absolutely stop at the center of the lens. They cannot go on, and it will be transmitted horizontally. No way do these meet in real life, so we're going to extend them backwards. And where the rays actually meet is where the image appears.